We're looking at Bayesian naive Bayes, and we defined our setup here for a naive Bayes model, and now we're ready to go Bayesian. So the first thing we need to do to go Bayesian is we need to put some priors. We need to put some priors on these parameters. So the first one is this pi. Remember our parameters here, our parameter vector was all these distributions. So we had pi for the y's, and then we had all these rjy's for each value of j and y, each dimension j, or each feature j, and each possible value of y. So we need to put priors on all those, and let's do that. Well, what prior should we choose? Since these are categorical, that's our assumption here. We're working with everything categorical, and of course, in particular, since it's classification, then all the y's are taking these finitely many values. So a natural choice is the Dirichlet prior. So let's make this a Dirichlet distribution. We write this for the shorthand for the density, and it's Dirichlet on pi with parameter, let's say alpha. And this is proportional to, so I wanted to choose a Dirichlet because it's a conjugate prior for a categorical distribution. And this is proportional to the product over y's from 1 to m of pi y to the alpha y minus 1. That's the important part, and then we can't forget the indicator function. The indicator that pi is in the probability simplex. Let me just put pi as valid to indicate that it's a PMF. And here, each of these y's, or rather each of these alphas, is strictly positive. So alpha y is strictly positive for all y. This is a vector. This is just a vector of alphas from 1 to m. And we also need for each, let me call it k here, r, j, and k. So I'll use k for the value that y takes. Let's make that also a Dirichlet. So we'll make it Dirichlet on jk with parameter. Actually, let's keep things simple. Let's just put the same, let's give these all the same parameter. So in order to do that, we need to, before we were assuming that these could be, each feature could take a different number of values, and I made these different sets aj. But let's just suppose that all these are the same. So let's just suppose that these are all just some finite set A. Maybe from 1 to, maybe this is the set from 1 to, I don't know, capital N, let's say. And this beta then is going to be, well, let me write here, alpha. Alpha was a vector from 1 to m. Each alpha I was strictly positive. And beta is going to be a vector from 1 to capital N. Each of the possible values that each feature could take, and each of the betas is also strictly positive. All right, and this is just like before. This is proportional to the product over, let's say, I don't know, let's say L. These are all the possible values that feature could take. L from 1 to capital N, rjk of L to the beta L minus 1 times the indicator that rjk is valid. All right, so those are our priors on those two, and to define the total altogether on theta, let's just say that these are marginally independent. In other words, this will just be the product of all these guys. Let's say, I'll just write it, product over all j and all k of, this is just the product over j from 1 to, 1 to d, and then over k from 1 to, what does k go to? 1 to m, because that's all the values of y. All right, so that defines our prior distributions. And all together, we have a distribution If you multiply the prior times this guy, we've got a complete distribution defined, a joint distribution. So that's looking good. We've got our model. And that was the first step we needed to do to be Bayesian, was to put down some priors. And the other thing we need to do to be Bayesian, to be fully Bayesian, is to just use the rules of probability. And in this case, what do we want to compute? Well, we're doing classification. So let's make a line here, separate. So that was all of our setup. And now we would like to know, in order to classify a new point x, we want to choose the appropriate y for that x. That's classification. And so we want to look at the probability, the predictive distribution, the probability of y given x, and the data. And now we're just going to use the rules of probability with our model and see if we can get an expression for this. And the beautiful thing is, with this model, the fantastic thing is that we will be able to get a closed form expression for this guy, which is really nice. Okay, so how are we going to do this? Well, let's see. The first thing, so I thought about this a little bit ahead of time, and it's a little bit involved, but I think that this is going to be the way to do it. So the first thing let's do is, let's say that this is proportional to, well, it is, this is proportional to this as a function of little y, because this equals this divided by the probability of x and d, and that doesn't depend on y. So we have that. And then let's integrate out. We need to introduce our parameters in order to use our model. So we'll integrate out our parameters. This is equal to, let me switch x and y here. X, y, d, probability of x, y, and d given theta times the probability of theta. And we're integrating over all of those prior parameters. This is an integral over all the coordinates of all of these different distributions, all of these different vectors. So this is actually a whole bunch of integrals here. But we'll just simplify it and write it this way. And now what do we want to do now? Let's use the naive Bayes assumption. We'll use the conditional independence assumptions here. That looks like a good thing to do. So this factors, because each of these points, maybe I should be a little more formal here. Oh yeah, I wrote it here. So this x, y, this is going to be, we'll think about the predictive distribution as being over these guys. This is just a generic one. And this is our data, and these are all conditionally independent given theta. So that means this factors probability of x and y given theta times the product over I from 1 to n, probability of x, I, yi given theta times the probability of theta. That's not in the product. So maybe I should put some params there. Okay, now let's look at, let's see, let's first look at this one. This one's pretty simple. We can just write down an expression for this one. This is probability of x and y given theta. We just defined this above, right? This was the thing that we defined here. And let's write it as, let's see, so it's the probability of y times probability of these guys, and each of these is this rjy of xj. So this is pi of y, probability of y, times the product over all j of rjy of xj. Right, that was what each of these was. But let me write that a little bit differently. Let me write that as, let me put a k here, rjk. I think we want to do this. we'll take the product also over the possible values of y. So as k goes from 1 to m, and let me put an indicator here. I'm running I don't quite have enough space. Let me rewrite that. It's rjk of xj to the indicator that y equals k. And that's true because when y equals k, then we just recover the original one with y here instead of k. And if y is not equal to k, then it's 0, so all those just go away. Okay, now let's look at an expression for this part here. So this product over i's of this thing equals, well, it's just the product of all these, right? Product over I, pi of yi times the product over j and k, rjk, xij, to the indicator that yi equals k. I'm dropping what the range of these products is. But you can always go back and check that, whatever it was, happened to be. Not particularly important. And actually, let me rewrite these in terms of, let me use our notation for, I think those will be helpful a little later. This is just a categorical distribution. This is, since we can write this as the categorical of yi given pi with parameter pi. And this is the same thing. This is the categorical of xij given parameter rjk. So let me write that. This is cat xij given rjk. Okay, that notation will be helpful, I think, in a second. And now we need to get an expression for the prior, and that's equal to the product by our model of the probability of pi times the product over all j and k of the probability of rjk. And each of these is a Dirichlet, so let's write that. Dirichlet on pi with parameter alpha times a product over j and k of Dirichlets on rjk with parameter beta. All right, now we're going to look at the product. So we're going to multiply this one, that's this part, times the prior. Let's look at what that is. Let's multiply those and see what happens. So let me call this, let me say, to be clear here, let's call that A. So A, which is just this part, equals, we multiply these two together, and what are we going to get? Well, let's start to pull things together, actually. We've got this part's going to go with this part, because it involves pi here and pi here. This part's going to go with this part, since they involve j and k, or rj and k. So let's go ahead and do that. Let's go ahead and say this is Dirichlet pi given alpha times the product over I categorical on yi with parameter pi times the product over all j and k of a Dirichlet on rjk given beta times the product over I, and that's this part, categorical xij given rjk to the indicator that yi equals k. All that together. Okay, now things are starting to look good. We'll be able to use the Dirichlet categorical conjugacy. That's what I was aiming for here. But I'm a little out of time in this video, so we will pick it up in another video, and we will work this out.